Welcome, everybody. We are 3 days away from research presentations. We have 5 groups working on their projects this week. And I know every project group working on texts, and our today talk, our today guest lecture will be very related to your projects, I think. It is a huge honor for me to introduce Professor Kemal Oflazer to you. He will be our guest speaker today, and his talk will be on natural language processing and computational social science. Kemal Oflazer received his PhD in computer science from Carnegie Mellon University in Pittsburgh, and his MS in computer science and BS in electrical electronics engineering degrees from Middle East Technical University in Ankara. He is currently a faculty member at Carnegie Mellon University, Qatar, and where he is also Associate Dean for Research. Over the last 30 years, Kemal Oflazer has worked extensively on developing NLP techniques and computational resources for Turkish with his collaborators and graduate students, and has published over 150 papers. Welcome, Kemal Hocam. The floor is yours.
Teşekkürler. Thank you. So my slides are English, and I was told initially that this would be sort of available to non-Turkish speakers. So I'm going to talk in Turkish, but if you otherwise prefer, I'm perfectly fine switching to Turkish. But at least let's go with English. So a little bit caveat, this is more like natural language processing than computational science, social science. I'm going to try to, at the end, point to a very recent activity that's happening in computational social science and NLP. So if you're interested in those things, you can further follow up. This is becoming a very, very active field. In fact, this morning I received an announcement for another workshop on computational processing of political texts. Anyway, so I plan to make this a rather fun talk with occasional checking on your Turkish or English skills. And the point being that, yeah, we can do those things very easily, but the machines can't. Okay, so let's go this way. Basically, this is a subfield of computer science that does 3 main things. Okay, one is enables human-computer communication. Currently, we use mouse or keyboards, which are totally unnatural for humans. Why? Well, because people couldn't do any better, and that was the medium. But you would rather talk and have the machine talk back to you, okay? Just like, I mean, we don't click on people when we communicate with people, so that's very unnatural for humans, okay? It enables or enriches human communication. Okay, so humans are the ultimate social animal, and language is the ultimate social medium. Without that, we wouldn't be us. So this enables and enriches, and I'm going to explain what those are. And then there's a lot of stuff that involve some work with language. Humans can do them, but are not as fast, mostly, and then usually not as accurate as machines. Okay, so we would like to build these systems that solve these tasks more efficiently and more correctly. Let me just for a moment indicate what it means. More efficiently means really fast at a very large volume. Okay. More correctly means, you know, humans, yes, they can do things, but They are usually sloppy. They miss some things. They don't get the answers right, and so on. Machines can do those better. Okay. So what do I mean by human-computer communication? You want to be able to dictate an email message, which I routinely do on both in English and Turkish on an iPhone or any mobile phone. All of these systems have reasonably accurate, useful parts that let you dictate email messages as opposed to typing really cryptically on those keyboards. Okay. You're driving and you got an email message. You want to be able to have the machine read that, but you want to read it so that it says the proper pronunciation, the tone, and the stress, so that there is no miscommunication. Okay. So that's a very useful thing. In case of human-human communication, the most important thing is really real-time text and speech translation. And these days, these are reasonably useful, so that you don't have to know, if you're in Finland or Japan, you don't have to know these languages to communicate, say, in a train station or in a restaurant, and so on. I have used these systems and gotten good food, so they work. Without that, we would be just using a bunch of gestures and this and that. This makes my communication with another human much more useful. Okay. You're in a meeting, there's a machine basically tracking everybody, what everybody says and so on, tries to analyze and then does a speech to text on these things, puts them in some kind of order, summarizes it, and gives you a summary of the meeting. Okay, that's again enriching a human-human communication. Or if you're communicating with speech or hearing impaired people, you could do machines that could sign. So that's text to sign. And so a deaf person can see. Or you could do, I think Microsoft has an app that if you put it in front of you and walk, as you go, it will describe what's in front of you by speech. So if you're visually impaired, you can still function. Okay, so those are additional help for helping with humans. And then improving the efficiency of tasks are typically, the mundane things. Well, it turns out this is not really mundane. Correcting typing and writing errors, and I separate those. Typing errors are typically, unintended things as we do as we write. Writing errors are typically have deeper reasons. Okay, sometimes you don't know the proper words, you don't know, you don't have, let's say, a good understanding of the language you're writing in, and so on. So the machine can fix that. For instance, Gmail these days, if you write an email in English, will try to correct your sentences, saying, hey, why don't you use this form? There are other tools like Grammarly that will do that. More sophisticated stuff are things like question answering, not typing keywords into Google and getting an answer, although that's a really important large-scale language processing. Question answering is more like how you envision it. You ask a proper question, and the system gives you one proper answer. Okay, so what's the height of Mount Kilimanjaro? And it says 7,000 meters or something. Not like a whole list of pages where you have to deep dive and figure out. Okay, or the machine reads an email and says, I can answer that. There are rudimentary versions of this in Gmail, where it gives you a set of options, just you click, and then that reply goes. Of course, doing a sophisticated response is still not even close. Okay, we're not there yet. So I think you're of an age where you have no idea what this movie is about, probably. Okay, so this was a movie that was made in 1968. Stanley Kubrick is the director, I believe. It was a cult movie at some point. Why this is important? So 68 is when the basic technology for internet was also deployed. So we're talking about 50 plus years ago, right? No, 50, 60, 50. Okay. So, so these people consulted with people who were supposedly doing computer science at the time. So the movie is 68. They said, what can we expect to have in 2001 in terms of this technology? How would computers be? So they got most everything right. This is amazing. They got most everything right. Okay. And with the exception of a couple of things, it was way more smarter NLP than NLP is now. So 20 years after 2001, we're not there yet. And they totally missed the mark on the size of the computers. The 2001 computers were huge. I mean, really huge, meters by meters machines. Now, even in 2001, everybody had switched to PCs, okay, which were probably more powerful. But they got most everything right. In fact, there was a workshop at MIT at about 1998 on the legacy of HAL, HAL being the name of the computer here, which is literally each letter is one before the letters for IBM. So the computers were actually, they didn't want to say IBM, so they chose HAL. And they basically said, okay, we guessed that these would happen. Are we close or not? And they were pretty close, 70, 80%. Well, we'll get to it, but the machine there, HAL, was able to beat a human in chess, which happened in 1998, if you're into that kind of stuff. It could converse, but it's not really what we have now. We're not even close to that sophistication. More importantly, it would conspire against the humans. So the computer got this wrong idea that the humans were trying to disconnect it. So it tried to conspire against the humans. So the human operator says, open the door, HAL. And in a deep voice, HAL says, I'm sorry, Dave, I can't do that. One of the most iconic passages in any movie I have watched. So it was a quote unquote intelligent system capable of basically understanding and generating human language. We're not close to that yet. And it could reason, it could do multi-hop reasoning, that are mostly associated with humans and so on. We're not there yet. I mean, we're sort of somewhere into it, but not there yet. Okay, I suggest you watch that. Okay, it's a space movie, but it's really about computer science, honestly. Okay. So I have a bunch of things here. What NLP does these days. Interesting things. I mentioned things like helping disabled people. Something that would be probably very useful for Turkish audiences would be watching a soccer match and summarizing the result in 15 seconds, so you don't have to watch the damn thing. Okay. You can do translation. You can, interestingly, you can grade exams and essays. So if you ever have taken an SAT exam, that's if you want to get into a US colleges, you write an essay. That essay is rated or ranked or graded by 2 graders, one of which is a machine, one of is a human. So immediately you're getting a 50% improvement in costs and efficiency. And the correlation between the machine output or machine grading is very, very high when compared to human grading. Okay, so this is really language processing that can provide substantial efficiencies, let's say. Estimating public opinions for social scientists, political scientists, and so on. You use systems for, especially in these days, we use teaching tools where students pose questions and you're supposed to answer it, or the teaching assistant answer, and so on. Let the machine answer it. Okay. We have done a little version of this for technical material in computer science. It works reasonably well. Okay. So, maybe we'll get rid of the A's at some point. Eventually, they will come for us. Okay. Some key applications, again, what we call open information extraction. Read some piece of text and figure out who did what to whom, where, how, why, and so on. Okay. Just that, unstructured utterance into some structured database. Of course, this is really, really, really hard. Okay. Conversational agents like Siri, Alexa, Google, OK Google, or whatever. I shouldn't be saying Alexa because there's an Alexa in the next door. I don't want it to wake up. It did one in one of my presentations. Question answering. This is, again, deep question answering, not just Google search. Image captioning. So this is very interesting. It's still a toy thing, but you show a picture and it gives you a sentence describing the contents. Okay, this is really camera to text. I mean, this was, when I saw this, I was blown away. It gets it reasonably good. Okay, you can search for it and see what kind of examples people do. Text and speech translations. Now it's become really, really usable, even between really distant languages. Which, why would you want to translate from Swahili to Mongolian kind of situations? You can still do that. Okay. Machine reading is basically reading whatever text you can get your hands on, typically news and so on, and internalize the contents in some form so you can reason. Okay, so this one is just basically one sentence at a time. This is like a more sophisticated linked concepts that you can navigate in a reasoning system. Summarization. This is the useful versions of these are available. I think there's one in Macintosh. If you use Macintosh, if you haven't discovered it, look for it under services. You can pick a web page and say, show me this thing in 10%. So I will give you a 10% version of it. Okay. Opinion and sentiment analysis. Lots of people want how they are doing in the marketplace, for instance. Banks and then companies such as Amazon, they would like to get understand how their products are doing, and so on. Along with that comes things like fake text identification. Okay, this could be fake news or it could be fake reviews. Okay, and then as you are getting better and better in detecting fake news, people are getting better and better in generating fake news. Okay, so there is that tension, which is very fast and affecting our lives in general, and probably contributing to a lot of social issues along the way. Okay. What do I mean by understand and generate language? Well, this is called NLU. This is sort of what we do when we are listening. Okay. Okay, so the computer would understand some input and would act on it. It's the acting part that lets us know that the computer got it right. Okay, there's no other way we can know that. We don't know how really what humans encode in their brains when they tell you they understood something. Okay, that's really not observable. Okay, so the robot understands and executes. You say move the red block on the left on top of the blue block. So if the robot does this thing properly, it involves other stuff than just NLP. Okay, then you said, aha, it understood what I meant. Okay, there's no other way of doing it, honestly. Generation is the reverse, is what you do when you are speaking. There's some representation in your brain that becomes into grammatical sentences in response to a previous interaction, language interaction. Okay, so you're supposed to communicate the relevant information, taking into account what the listener also knows. You don't have to repeat everything, right? We maintain some information, however short term, so that the conversation can go on, quote unquote, efficiently. Okay, so reading an article and generating a short paragraph is really an example of that. Okay, here is this is actually pretty old. It's about 7 years. It basically takes a computer generates a text for a news article by just looking at company financial reports. So it takes an Excel spreadsheet and writes that text for you. Okay, apparently that's how these things are reported. Okay, there's a certain flow onto this. There are certain things and there's a sort of order in which you describe stuff, and then maybe there's a paragraph that you sort of put your summary and conclusions in. Okay, so newspapers such as New York Times or Wall Street Journal or those, if they have something on their website that is like this, and they can generate it essentially using a computer in 5 seconds, they would rather use that. Okay, so we hear these things, NLP and AI. So NLP is really a fundamental problem in AI. AI is kind of more general, but NLP is a substantial portion of it. Okay, so there used to be this thing. Well, people discuss whether it's still a test or not, but Alan Turing, who is really sort of associated with a lot of very seminal work on computers and computer science, proposed a very supposedly simple test, saying, "Hey, you have two screens that you can communicate with two different machines. You have a keyboard, a screen, a keyboard, and a screen. Okay, you're communicating with them. You don't know whether the other side is a machine or not. And you have to ask questions, and you get answers. And based on the answers you get, if you cannot discriminate which is which, and if one of them is a computer, you can say the other one exhibits intelligence." Okay. Now there's a whole philosophical debate behind these kinds of things. There is a famous Berkeley philosopher, David Searle, I believe. He says machines don't understand. although it's not clear what understand means. Okay, what happens when we say we understand? Well, I have no idea. Okay, and that's a philosophical problem. I won't get there. So in computer science circles, we call NLP kind of affectionately AI complete, meaning you can't do NLP unless you solve all the major problems of AI. So it's a chicken and egg problem. Okay. Other fields, machine learning, AI, statistical modeling, information theory are really, really technical fields that provide the formal tools. So it's mostly mathematics, I mean, heavy-duty mathematics in the case of machine learning, and statistical modeling, information theory, and then understanding human-computer interaction. And then, by the way, NLP is not a theoretical discipline. Okay, you cannot just say wave your hands and we can do this way. No, you have to build a system, and that system is a lot of software. So it's software engineering. These days, you have to be careful about the ethics of the work you're doing and ethics of your data that you learn from, and so on. And then cognitive science gives you windows into the human mind as the mind processes language, for instance. Maybe you can get some understanding. But we're building planes. We're not trying to understand how birds fly. Okay, so it's not terribly directly relevant. Okay, logic, lots of logic, and then language is a social construct, right? So social sciences, political science, psychology, all kinds of things come into play as potential application areas and source of problems that maybe people haven't figured out that they should consider here. Okay, so that's what I'm seeing as I was going through the proceedings of several of these workshops, that's saying, interesting. Notably missing here is linguistics. You might just be thinking, so what happened? So linguistics, I'm going to talk in a few moments in detail, but people have given up on linguistics when they're doing NLP. Okay. So I just talked about this part. Machine learning is really a general technique. There's nothing special about machine learning and language learning or languages or deep learning. So these are just general techniques. And it turns out that you can do everything in language processing better if you employ machine learning versus hand development, rules writing or stuff like that. Okay, so that's a technique. It's not the end. Okay, it's something you should know when to apply and how to apply and what to expect, but it is not an end in itself. Okay, so machine NLP uses these techniques amongst others. Okay, so and then linguistics. So linguistics tries to understand how the brain produces language and what is the general structure of all languages. Okay, why do we have a grammar? Why is grammar useful? Why can't we just like randomly spit out words? Okay, and so on. So they try to understand why certain languages have certain properties, why those properties, maybe there are 5 or 10 different sets of such properties that make each language unique. Okay, now Turkish has certain properties that English doesn't have, and vice versa. Why do these? How did these develop and not others? Okay, there were, I don't know, 7,000-8,000 languages that human communities have evolved over the years. They try to understand. They don't really deal with language as it appears in real world. They assume ideal languages. Real language is really, really, really dirty. Okay. We use intonation, we use gestures, we use things like I mean, you know, stuff that are really not contributing too much to the informational content, which you don't find in texts, for instance. So they don't really terribly concern themselves on those things. So let me just give you several applications here. Let's see if the Turkish speakers get what's going on here. So here's a piece of text I got from some source. I corrupted it intentionally to make this example. So there are a lot of errors here. And you have to really read carefully to figure out where the errors are. Okay. Let's see if somebody gets something, and then I will give you the answer.
There are some missing characters. And
there's one missing character, two missing characters actually.
And some characters are changed, like capital, they become capital.
Like what?
So there are many capital characters starting. Each word is starting with a capital character.
No, that's actually perfectly legitimate.
I believe ziyaret and
so ziyaret is a typing error.
And zeytinyağında is another one.
Zeytinyağında that's a general educational lack of education on the side of like the last two generations in Turkey. Okay. Nobody in my generation would get that wrong. Something happened along the way. Okay. İşaret alınmasından. So alınmasında is a perfect fine word, but that's not the right word in that context. Everybody. So the subject of the sentence is Reşit Özer, which means this should be belirtti, not belirttim. Okay, so, and then the proper form of the causative of artmak is arttırmak, not arttık. Anyway, so you get the idea. So only one of those is really a typing error. The other ones are otherwise perfectly fine words, which just are not supposed to be used in that context. Okay, that's a very hard problem. Okay. This is a canonical example I use all the time. Okay. Find the funny error here.
Word by word translation, and then
Word by word translation. The guy looks up
wrong translation as well.
The dictionary çevirme is also translate, so he says you can translate. Okay. Of course, he's totally ignoring the context. Okay. Context is the most important thing, it turns out. Okay. Interestingly, though, humans do it effortlessly. That's what we're doing now. I'm speaking. I'm not really speaking very slowly, so you can understand. We're just doing this normally, right? Furthermore, we learn to do it effortlessly, even in multiple languages. Okay? So clearly, the human machinery is extremely good with this. Okay? And clearly, the non-human machinery is not yet there. Okay. So what does the following sentence mean? At last, a computer that understands you like your mother. This actually was an ad from 1980s when they were trying to sell you PCs. Okay. So the intention is rather clear, right? Computer understands you as well as your mother understands you. That's the intention. Okay, but it can't. Okay, why not this one? I mean, there's nothing in the text that says this can't be a meaning. Or this one. Problem is ambiguity in human expressions. Okay. What does that mean? Empty when full. Is that a contradiction or is that something else? Okay. You have to think about it for a few seconds before saying, aha, that's what they mean. Otherwise, that's just total nonsensical. Let's see how you fare. That's the sentence. Now, we're going to find different interpretations. Some of them will be totally ridiculous. But nevertheless, when it is explained to us, we can say, yeah, that under that circumstances, I could use this sentence. Okay. So we have that one. So can somebody give me an interpretation? That the most salient one in this case.
It's a sentence describing how time
flies, right? It's really going fast, right? That's the intended interpretation. How about the second one if you push it a little bit?
It is telling us something about a species called time flies.
Interesting. That's coming later. Okay, so it's an error to you. Sorry, an imperative to you. You have a stopwatch in your hand. Your timing flies as they pass, as you time passing by arrows. Okay. Here's an arrow. Stop. Stop. Okay. That's ridiculous, I know. Okay. But if once I give you that, you can say, aha, that could be interpreted in that way, right? Now we have an arrow doing the timing. Okay. And we're trying to ask you, you should time it as arrow would time them. Another ridiculous interpretation, but then there's nothing. Now that I explain it to you, you can say, why not? Now maybe there is a species of flies called time flies, and they like an arrow, as in fruit flies like a banana. Okay. And then the fifth one is what I believe Yasemin mentioned is time flies like an arrow. That's really with the exclamation mark, saying, hey, all these time flies, you should like an arrow. Although liking is not necessarily an imperative verb in a sense. So you give this to a machine, and how do you pick the correct one? That's very hard. I mean, very, very hard. I mean, yet, the moment you see this is the first one. The first interpretation is what you focus on or converge on. Humans use common sense. I'm putting that in common in quotes because it's really hard to formalize what those are. Okay, common sense, bits of culture, world knowledge that sort of permeates from our experience. Okay, to support the language faculty. Okay, language faculty without vision or other things are not very useful. Okay. We wouldn't be able to learn language if we did not see things. you know, your mother says, eat that apple. And if you can't see the apple, you can't figure out what an apple is, as other than it's a piece of sound. That's, yeah. There's a lot of work on these things, especially in AI, but very, very hard. Okay, you have to write down a lot of differential equations to tell a computer, if you drop something, it will go down this way, not up. Babies learn this when they're age 1. Hey, if I drop something, it goes down. Okay, I don't have to talk about gravity and other crap. So the package did not fit in the box because the package was large. Package did not fit in the box because the box was small. So there's nothing in the grammar of these two sentences. They're exactly the same except for large and small. Okay? They're exactly the same sentence. The grammatical structure, the words, etc., are the same except for those two. But you know exactly what is meant by each. So you're doing kind of an extra grammatical, extra linguistic reasoning to figure out that in the first case, it's the package that is large. In the second one, the box is small. Okay, that's not a linguistic problem. That's not a problem that NLP by itself can solve. Okay. Ambiguity in acoustics. This is, you know, speech. Typical speech processing systems, they, you know, you get some human acoustic utterance. These are essentially air waves, right? Hitting on your drum, eardrum, going through the 3 bones in the middle ear, the cochlea, and so on, and creating signals in your brain. And some magic happens there. I don't know what it is. We have to simulate that. And then we say, those sequence of air waves is corresponding to that text. Now, when you speak certain phrases fast enough, that stops being unambiguous. Okay, so understand you like your mother or understands you like your mother. Okay. It's hard to recognize speech. It's hard to recognize speech. Okay, you clearly do not think about the second one ever, but the machine does, unfortunately. And you cannot write, hey, in this case, it's not recognize speech and a bunch of other rules. That's a never-ending task. Here's an Turkish example. Okay, again, in Turkish, we don't speak really slow. We assume people cut up. So if you heard things like "Evimneyle kaplattın," you could be hearing this one, but really no, because you don't cover houses with, you know, mother of pearl or whatever. Okay, but rather it's a question that is like this. Okay, speech has a speech segmentation problem. Where do we start and end words? Okay, because again, as I was jokingly doing, we don't speak slowly just so that the other person can understand. Okay. Now a quiz for Turkish speakers. Again, I give you the word koyun. I need what you think about the word.
Maybe
possible.
To put can be.
Okay, so hold that thought for a second, because that's a different, as a very interesting aspect. Okay, so the first one is either this or that. Okay, I mean it's the same. It's what we call a homograph. Words written the same but have totally unrelated meanings. Sheep and bosom. Although the bosom is rarely used in that form, we all say koynunu, koynuna aldı, etc. Okay. So that's the first one. The other one is what? Come on, almost all of us are native Turkish speakers.
It can be at the bay, like koyun, deniz koyu.
So that's the third one, but your bay, senin koyun çok güzel. So you all have koyus, right? And so on, right? That's one interpretation. The third one is what the other answer was. Koyun rengi çok güzel. Now, there's the two parts are really fundamentally different, meaning-wise. Because of pronunciation constraints, the N at the beginning, we just drop that, so they sound the same, koyun. Okay, so that's that. The third one is what Özgür said, the imperative, koyun. Okay, so these are literally the same root word and same morphemes, but this is a noun, this is a verb. And there's a fifth one, which
Colors, maybe.
yeah, but that's a kind of a forced, really hard to come up with a good example. Example, your dark one. Okay. Yani ikimiz de aynı elbiseyi giyelim. Sen açığını giy, ben koyunu giyeyim. Or something like that, right? That's why I put it in sort of gray, just so it's iffy. How do you know which interpretation to use in a given context? Or, I mean, you see this word in a context, like the koyun rengi güzel. Which one do you pick? Because that's how you do further processing to get the proper meaning out. Okay, so that's really tricky. A lot of statistics are needed there. Which of these is pronounced differently and why?
Verb, probably.
Which one?
Verb one.
This one.
Put meaning.
Yeah.
Yeah.
Yes, because Turkish has a fantastic stress system, which I sort of learned after I was 45. I was like, really? We do that? So the stress here is on the first part. It says koyun, not koyun. Okay. That's why text-to-speech is not really text-to-speech. There has to be some deeper analysis that this word is a. I mean, there's examples of these kinds of pronunciation differences in English. So you play the bass, but you eat the bass. Or every minute animal takes a minute. Okay, so depending on the meaning or the grammatical category of the word, pronunciations may change. In the case of Turkish, there's a lot of changes in stress. Okay. Ambiguity in sentence structure, we gave several examples before. Okay. You know, here is one way of grouping parts of the sentence leading to one meaning or you can group them in some other way leading to another meaning. So that's very, very prevalent. Okay. The last 20 years, 25 years of computational processing of computational extraction of the structure of sentences has been trying to solve which structure is the correct structure. Okay. And we know how it works, but it needs a lot of data that is not hard to come by, especially for languages like Turkish, although early 2000s, we built a data resource for these kinds of things called Turkish Meto Sabancı Tree Bank, which actually helped a lot, but the size wasn't important. It was not sufficient, sorry. Ambiguity in word meaning. Knows you like your mother. Okay. That's probably what you mean. But it turns out in the dictionary, there is another meaning for mother, which is a big barrel for making vinegar. How that came to be, I have no idea. But the machine, without any access to statistical information, says, yeah, I have two options here. I need more things. Okay. Or we put our money in the bank. Clearly, we're not burying the money in the river bank, but rather putting in a financial institution, most likely. This is known as word sense disambiguation. It is a problem still unsolved, without much hope. And humans do this effortlessly. I mean, this is one of those things that still shock me that we're not making any advances in this. Okay. Ambiguity in discourse. Leila says they're selling a computer that knows you like your mother, but she, and then there's something else coming on. So what does she refer to? Is it the mom? Is it the computer? Is it Leila? Okay. So this case where you are trying to combine or conflate information from a sequence of sentences that are naturally following each other in a discourse. So this is processing beyond one sentence. It's called discourse, and discourse is really the edge of stuff now. We're not anywhere close. Okay, doing that. Although a lot of activity, especially for people developing these tools like Siri and so on. Okay, so let's disambiguate once more. Okay, so you probably have a feeling as to what's going on here. Now, this one, in here, many of the words have competing senses or grammatical categories and so on. That sort of plays with your mind. Okay. So I'm taking suggestions here.
I see 3 possible meanings. One is I saw her duck go down, or 4 with it. Well, the duck was holding a telescope. I saw her duck with a telescope while I was looking through a telescope.
Good.
I saw her duck, the actual duck with
The
a
animal.
Telescope.
Yeah.
Yeah, the animal. And yeah, so
that's
4
pretty
that
much that's pretty much most of it. So duck. So you're using a telescope to see her duck. That's one of the interpretations that Benya gave. I saw her duck that was carrying a telescope. So it was the duck, little luggage, and then bag and carrying a telescope. Maybe, of course, our world knowledge, quote unquote, says, yeah, that's bogus. You shouldn't be thinking that. I use a telescope to see her ducking, basically just going down fast to evade something. Okay. I saw her ducking while she was carrying a telescope, or I was carrying a telescope. So has a third meaning or second meaning, like you're cutting her duck with the telescope. Clearly, that's again bogus. But that is the second meaning of the word saw. So the past tense of the word see is the present tense of the word cut with a saw. How did that came to me? I have no idea. Languages do strange things. But look at the following sentence. suddenly you don't feel like there is more than one interpretation. Although the syntactic structure, the sort of word by word, is exactly the same. Okay, it has things like telescope is something you can see. That sort of kicks off a bunch of things. Okay, while pencils are not things you see with. Okay, so those things are all. Language is evolving. That's the blind side that hit everyone in the last 20 years. Okay, internet comes in, massively user-generated text, generated by people who have no clue what language is. They write badly, okay, and then they are lazy, so new languages emerge. Okay, so then we start using "oh my god" and LOL and whatever, and then the emojis. Emojis are actually earlier, and then hashtags, and then hashtags, like you have a whole sentence with all spaces thrown away, and now you have to figure out what the damn words are because the guy is too lazy to not write a hashtag, and so on. Okay, how do you deal with this crap when you're processing tweets? Okay. What we write is becoming shorter and shorter. Probably the information content isn't terribly high. So we started with web pages, then we had blog posts, and those too much to read. And then people started Facebook posts that were still non-trivial amount of text, and then suddenly like it's 280 characters or whatever, everything. Okay. Another thing is interacting cultures and languages led to something called code switching. Okay, this happens when you have a non-trivial immigrant or second language, different language minority in a country, and then the languages interact, and then you get things like "Zaten ich keine Schule habe, çok faal oldum ben ya." Okay, this is from Özlem Çetinoğlu, my ex-PhD from Sabancı. So this happens in Arabic speakers, usually for other reasons. Arabic has a different interesting thing. It's very hard to write official Arabic with the Arabic letters, so people try to mix Arabic with a Latinized Arabic called Arabizi. Also, there's something called the Modern Standard Arabic, which no one speaks, but everybody writes in. Okay, it's like it would be if we did it, it would be the Modern Standard Turkish, which all the Turkic countries would write their official documents in, but everybody would speak their own language. So the Arabic in Morocco is mutually incomprehensible with Arabic in the Persian Gulf. Yet they can both read Modern Standard Arabic. Now, when you take that Modern Standard Arabic and you're in Tunisia, then French gets in. So you have half the sentences in Arabic, half the sentences is in French. Okay, so this is happening when there are sufficient momentum in the languages so that they kind of interact. By the way, I mean, this is a perfectly fine. So it's not like it's a random combination. You don't mix these things. How do you deal with this, especially when you have some people write these things on social media? It turns out there was a paradigm change in about 1990 where people said, okay, the whole thing with writing grammar rules and so on is a losing game. They said we have to use statistical. There was actually some speech recognition work that was happening at IBM Research in late 1980s. And the guy who was running it is famously rumored to have said, every time I fire a linguist, the performance of the system goes up. Okay. So that, although he denied having said that, that actually turned out to be a very, very correct observation. So what do I mean by statistics and language here? Okay, so you see the word "the," what happens? You have no idea what the next word is. Most everything in English can come through here. Then you see this. Now suddenly you have a few options. Okay. Okay, so I'm taking bets here. What's the next word? Come on. Hint.
Life.
Life. Right? So given 4 words, you can predict the 5th word pretty accurately. Right?
Speech.
Well, something has to come before that.
A speech.
A speech.
Good.
Address.
Address, ultimatum, anything that, by the way, you wouldn't say the prime minister gave an apple. Although it will be perfectly fine, you never have read a piece of text where a prime minister gave an apple. So that would be very low on your list of options. Okay, so suddenly you see that you match some history to what you have seen in the past, and now you can predict what you can see next. Okay, that's the big idea here. Nothing terribly deep. Okay, how about this one? Of course, at this point, you can figure this out. Okay. Now, what is another interpretation that can come after here that we haven't, probably not terribly Turkish-centric, but the prime rib was, what are typically prime ribs?
Delicious.
They can be delicious. Okay, not blue. So the chance that blue will come after these is really 10 to the minus 65 in probability. Okay, so so basically the whole thing is, given a piece of context, can you predict the next word? Okay, so this was about 10 years ago I got these numbers. But if you look at the if you could search Google with the exact phrase, and it would give you how many times it appears at the Google databases then. So the prime of his life. Okay, so women didn't have primes, I guess, at the time. Okay, not many, almost half. The prime minister, a lot of times. Without any further context, the prime minister in any arbitrary text would refer to who? So
Boris Johnson.
The British prime minister. So if you read New York Times or whatever, if they use prime minister, it will be the British prime minister. Okay, not Canadian, not Australian, not any other. Okay, that's how it is. Prime minister gave no, it's like going slowly down, right? Gave an okay, the prime number, the prime rib was delicious. Prime rib outstanding also could be smaller number, but blue 0 times. You can't find any text on at the time on, so that's why you never think about it, because you never saw it. Okay, so that's sort of the gist of the statistics part. Okay, we have a lot of internalization of what we hear, what we read. We kind of create an internal model that we actively and really quite fast use. Okay, so the computers can suck in billions and billions and billions of words. Okay, and then compute statistics of which words follow which words and build really simple statistical models that can do predictions of the sort I covered. Okay, so if you want a machine to complete a sentence, like the US president, okay, you have to fill in the next word. Typically, even after a while, Obama is the most likely choice. Okay, but basically, it doesn't have any knowledge about US presidency or history or politics. Okay, it basically says, what is the conditional probability of this word appearing after these 2 words? Okay, note that Blair has been shown after that, has been seen after that, but extremely low. Okay, so you would find the maximum here and just report that. There is absolutely nothing else, nothing deep going on. Okay, so this kind of thinking, that is finding some probabilistic representation of the options and then picking the one with the highest probability, is literally the only trick we use. Okay, I mean, I'm not downplaying the complexity of all these things, but that's the big picture idea. Okay, so how do you hallucinate text? Okay, so I'm going to explain. So you start with a word and you keep on picking words based on statistical relations, nothing else. Okay, so I give you a history, you pick the most likely word that can be generated randomly. Okay, so I'm basically checking using a probability of a word and history, given a history, and I pick that word randomly. How do I do that? Like, remember the prime example before? Same idea. Okay, so I put all the words in a linear line. Okay, and the distance between a word and the previous word on that line is proportional to the conditional probability, conditional probability of that word. So you take a dart, throw a dart on that line, okay, and wherever it falls, that's the word you choose, and the chances that it will fall just before a word is proportional to the probability of that word, because there's more space there so that it can fall onto that. So no history, you just randomly pick words. Okay, you get garbage. Okay, so that's not very interesting. I give you just one word immediately preceding, and then you pick the next word conditional on the previous word. Okay, you see some reasonable looking pairs of words. This is, I don't know where the source of this. I mean, I don't even understand why the Metos Sabancı tree bank actually is generated, because this wasn't our text. This was some random text. So this is, again, pretty garbage, but then we have things like online algorithms are also being completely surpassed in performance, etc., can achieve. So there is some rudimentary thing. Oh, this was, I don't know what happened here. This is, you look at the two prior words. So you're given the two previous words. Based on those, you predict the third one. This is now significantly better. Okay. Although totally nonsense, probably. About 20 years ago, there was a website at MIT where you give 5 keywords. It would generate an extremely good-looking paper on computer science that you could submit to these predatory conferences to see if they would accept it or not. They actually were accepted. The paper made absolutely no sense. Okay, but it read perfectly fine. They basically use that system, used to called CS paper generator. Unfortunately, I don't think it's still active, but it was hilarious. I mean, it made for some good humor. Oh, okay, sorry, my bad here. Okay, now the state of the art, say as of last year, is something called a transformer, where these computational devices have been fed literally 1 trillion words or so. Whatever it is, we don't know. That Wikipedia isn't terribly large by these standards. Okay, so Wikipedia, New York Times, all the newspapers around the world in English, whatever, right? So you basically give them a piece of feeder initial text, while not normally known for his musical talent. Elon Musk is releasing a debut album, and then you say generate, and it generates the text here, which is not that bad. Okay, so I tried this with this. By the way, you can start with the same beginning and then continue and generate another. It would just randomly pick another one. But hey, it looks quite good. So I wrote this yesterday. We're giving a talk on natural language processing about applications in social sciences, continues, and public policy. At the center of what we're going to talk about is news, what we know, blah, blah, blah. Come on, I mean, you could be convinced that this is a legitimate text that somebody wrote, okay? That's where the whole thing with fake news generation came into. These people who built this were really reluctant to release this for public consumption. They were fearing that people would generate all kinds of weird stuff. So they limit you on what you can do with this. So basically, I gave this example earlier, right? Understands you like your mother versus understands you like cured mother. You try to find whether this sequence of words has a probability, and it has to be much, much less than the probability of this one. Once you compute the probabilities of this, you pick the one with the higher probability. That would immediately, okay? How we do that is technical, no big deal. Okay, any questions so far? Okay, let's go for another 15 minutes and maybe we can take a break now. Would you prefer that?
It's all up to you.
I can go easily another, I don't know. I don't have to stop, but if people want to take a break, it's fine.
Do you want a break? Just put your void on chat.
Okay, let's then do with 5 minutes, and then we come back at 11:20.
Okay. 5 minutes break.
Okay. Okay, so here's a problem. It's a very general problem. It turns out, especially for social science applications, is document classification. I have a document which is a bunch of words, and then I need to put this document in one of several classes. Okay. So, you know, I get emails. Are they business, traveling, teaching, research, other types? So maybe I can you know, pre-process them so that I can look at them at different times. Are they spam or not spam? That's another thing. So the Gmail does that pretty good, classifying. But then there are documents at the borderline, you know, are always tricky. People who send you, for instance, spam, knows what these detectors look for, so they try to evade that. So, you know, you can have these words, but they don't necessarily imply that this is spam. Although most emails you get from that starts with some word Nigeria, for instance, end up being they want to get your money. They try to replicate spelling errors in humans, so the words may be whatever. So the point is, you can take a news article to tell me whether this is a sports, political, economics, etc. You can take an email. You can take a review of something and whether it's a good review or a bad review. So it's all these things are what we call classification problems. Okay. Simplest thing is what we call a naive Bayes classifier. We don't want to understand any of the grammar, any of the structure of the words. We treated the document as what we call a bag of words, meaning, hey, there's these words in there. Some words appear multiple times. We probably should ignore words like the and a and on and in. They're not terribly useful. And we look at the content-bearing words and so on. And then we look at a bunch of examples. When I say bunch, I'm talking about thousands or tens of thousands. And then we look at, you know, what's the chance a given word appears in a certain class of documents. So we build a simple model. We have C classes. Apologies for the typo there. C classes. So C is spam or not spam. C equals 2, right? But if it's news, maybe there are 10 different categories. So C is 10. Okay. So somebody gives us a new document. There are just N words in that document. We don't really care how the words are, in what order, whatever. And we try to find which class does this document D belong to. Okay. So we basically try to find the following probability. Given that document, what is the probability of a given class? So I put spam here, and the document, my model gives me a certain probability. I put not spam there, given the document, it gives me a probability. Then I pick the one with the maximum value. That's as simple as that. Okay. So here is a, you know, legal document classifier. So somebody says, hey, I got these million documents, and here are how I classify them. So there are maybe 10, 15 of these classifications. You go into what we call a machine learning system, you put these in, it builds a legal document classification model. So that's the capturing the relevant aspects of the words and their relationship with the class, okay? Which is mathematically, it is really nothing terribly deep, but it's something that captures the relevant information in what we call the training set, okay? Then you take that model you go to a new application. Now you have new documents coming in, and you want to put them into this classifier. The classifier says, hey, this is how I should classify, or based on this model, takes the document, looks at the words, runs through the model, and says, here are the probabilities of different outputs. And this one seems to be the largest one, so I pick that class. Okay. Very, very simple conceptually, and very, very simple to implement. In a natural language processing I'm teaching, this is like the second homework. They try to train with 50,000 documents. They manually classify 10 documents to see how hard it is for humans to do this because of the edge cases. But they typically get about 92, 93, 95% correct for previously unseen documents based on spelling correction. So you see this, you have different ways you can replace this word, which is misspelled. Okay, and there is only like one error, right? There's an extra letter or a missing letter, or two errors, and so on. And you basically look at what is the probability of school after arrived at. So that's history and the option, history and the option, and so on. And you pick the option with the highest probability. Okay. But then we have these cases which are typically made by really bad English speakers in American high schools. They don't know which principle is which. So all the words here are correctly spelled, but not in the right position. Okay, this should be spelled as that, and that should be spelled as that. Okay. That's a harder problem. Finding proper names in texts, easier said than done. Okay, so George Washington is a person, so you have to figure out the type and the text span. Then you have George Washington University. Well, that's actually a university, not a person name followed by the word university. And then you have George and Washington. So typically you build a statistical model of what comes before, what comes after, although you don't know what comes in the middle in general. Okay. So for instance, DR could be either preceded by a location name or followed by a person name, in which case they hint at either of those. Dr. John Doe has an office on Rodeo Drive. Okay. Question answering. So this is basically, where is the Louvre Museum? Paris. Where is the entrance to the museum? At this point, I'm also assuming that I just mentioned this one. I shouldn't be asking here the Louvre Museum in Paris. It's obvious from the context. Okay. And this is reasonably advanced, that machines do it at on standard test sets. Machines do this at about 93, 94% correct. Humans are about 3-4 points less. Okay. And that's a typical course project in a natural language processing course. So what I do is I give a Wikipedia article and then ask questions, and they're supposed to find the answer to that question in that article. So the search space is limited. Summarization, I think I mentioned this enough. I'll pass this quickly. Challenges for non-English NLP. Okay, so we saw some example in Turkish. We can chop different things up. So Turkish is notorious for having the generative capacity to create really long words. Every Turkish speaker would understand this, would probably never use it. Okay. But languages like Turkish, Finnish, Estonian, Swahili, Hungarian have this word formation processes, okay, which other languages, like many Indo-European languages, don't have, okay? So you have to deal with that. The reason there is Finland there is just, it happens to be the longest country name after the demise of Czechoslovakia, okay? So, well, what do you do with this, or a word like this? You have to sort of figure out parts of it. So I did color coding to help you with this. First, you separate what we call the morphemes, the subparts. Okay, so there are all these things. They come in a certain order, very specific order. If a Turkish speaker sees something out of order, then they will just like, it will hurt in their brains. Okay. And this kind of means the following in English. Again, color coded. Okay. And it looks like the English version is kind of a mirror image of the Turkish version. Okay. I have other material that you can refer to if you like this kind of fun stuff. Okay. I already did this. What is this? Okay, so Chinese, when they write, they don't have spaces. You're supposed to figure them out. Remember the Turkish example, evimi neyle kaplattın? Okay, that's Chinese all the time. Chinese do this effortlessly as they read. Okay. Again, machine learning. You basically feed a bunch of these characters, the kanji characters, okay, and you tell them whether there is a space or not after each character, so it learns where the space is after. So the statistical problem is, hey, if I see you, if I give you the previous three letters, can you predict if there is a space after the third one? It's a prediction problem. Okay. Japanese, they deserve the pain, I guess. They use 6 alphabets. Plus, they use vertical, horizontal composition. That's why I was trying to learn Japanese on Duolingo. I said, nah, I'm not going to go there. Okay, they use kanji, they use hiragana, they use katakana, they use furigana, and then Arabic for numerals, and then Roman letters for other stuff. Okay. Arabic, most vowels are not written, meaning long vowels are written, but short vowels are not written, and everybody has no problem. They keep on doing this, but it takes a while to learn this. That's how they used to write the Ottoman Turkish, which, you know, good riddance, okay, because that sort of is problematic. Machine translation. So we'll do machine translation in a moment. Basically, the idea is you have text or speech in one language. We call that the source language, and you try to transform it to text or speech in a different language called the target language. That's the simplest definition. And the constraints are you preserve, quote unquote, the meaning. The guy says, I ate an orange. You don't say the car is blue. Okay. So you're preserving the meaning. Plus, you want the target language to be grammatical, not just a word salad. Although native speakers of the target language could be, you know, could deal with the ungrammatical. You can say, ben var shish kebap yemek. You know, we understand what the guy is saying, although it is not proper Turkish. Okay. This has been the holy grail application since the middle of 20th century. The goal was really to translate Russian physics articles to see how they were doing towards a nuclear bomb. That was the original motivation, by the way, not any other thing. This is an extremely hard problem. 2 major paradigm changes happened. One in 1995, that was the switch from rules to statistics. Okay. And then around 2015, the deep learning neural networks and lots of data. Okay. There's absolutely no linguistic analysis going on. Absolutely zero. Okay. As I said earlier, it is a reasonably usable state. I'll make comments on it in a few moments. Quality of the translation is an issue. Okay. It turns out there are automatic ways of evaluating that. There's one paper that came out in 2002 or something. This is how you evaluate. And then the field just exploded because then before they had people evaluating even translations. Very, very slow. Now you can evaluate 1,000 times a day by tweaking your system. Okay. Speed, way faster than humans. Literally about 100 milliseconds a sentence these days. Okay. So if you can use Google Translate to get the gist of a news article in a language you do not know, if you want to interested in, like, summary of a soccer game between Bayern Munich and whatever, you can read it and you probably will get the idea quite right. You can communicate in restaurants, typo there, train stations and so on, perfectly usable. Okay. You don't want to use it for legal text, or you don't want to translate it an F-16 fighter plane maintenance manual and give it to a technician and saying, hey, use this. If something is wrong, and the plane may fall, and that's not good. So for these kinds of applications, it's still not there. Probably will not be there for a long while. Or for literature translation and stuff like that. Still, I mean, like novels and stories and so on. Look at the following for a few minutes. See the problem?
It's sexist. Really?
So, doctors are he and then nurses are she. Okay, why is that? So English has two genders, or three. Turkish has no gender. Okay. So essentially, the Google Translate is throwing a coin here, tossing a coin. Is it a he or a she? Sometimes it really comes back to you and asks, well, what did you really mean? Which one is which? So that they learn. But it turns out in the data they use, there is significant bias. Okay. Whenever they see doctors, they are always men, and when a bunch of nurses, they're all women. So statistics now comes and bites you. Okay. Going the other way is probably the other way, easier. But this was a problem. It was actually, Turkish was used as an example of Google screwing up. There was a huge backlash, not in Turkey, by the way, but in other places, saying, hey, we have to worry about the bias issue here. You cannot just take random data and put it in. So now people are, when they have an example sentence, they try to generate variants of that sentence with different genders, or whatever that thing changes in that language, so that they have a more balanced training data. Okay. Just to see again, non-Turkish, non-English NLP. How does English become Turkish? Okay. Very different languages, right? So you have to be seeing some pattern like this in English. And I color-coded for your convenience here. Now, this that means there can be arbitrary other stuff in there. Okay. Okay. Now you take this one, you do some kind of shuffling in essentially mirror imaging in sort of in the middle. Okay. So all the way strong comes here, become comes here, be able to goes here, make and so on, right? And then we replace each of these with the relevant Turkish translation, and then we have to attach them, and we get this one. Okay. Now, machines will not easily get that. They try to find that and directly go in here. Most of the stuff that you see Google generating in Turkish, they get most morphology okay, but not the more edge cases correct. Languages are different. Okay, so if you're going to learn this, you have to learn to distinguish these things. So there is, English is subject, object, subject, verb, object. Arabic is verb, subject, object. Turkish is subject, object, verb. But in Turkish, anything goes anywhere, depending on the context. Okay, so certain languages have Wann and Mauer, for instance, in German. Okay, now the translator would not know whether you are in the room or outside the room, so it will probably throw a coin and pick Wann or Mauer, or Mauer, by the way. Sorry. Runway in Dutch is a landing runway and then and take off runway. Different words, and so you have to figure out what the plane is doing in Dutch. Okay. Other examples there. Different languages cut concept space in different ways. This is French and English. Okay. So how leg overlaps, how foot and paw overlaps with different concepts here. So all this actually could be captured by statistics. You would not believe. Okay. We don't have sometimes a word in a language, and so you have to make up stuff. So there's this Japanese word called oyakoko. Okay, you don't have a word for it. You have to explain the damn thing. Or gurbet. It's where you are not at home. Your home could be your physical home or your country, home country, or home city. Okay, I don't think any European language has that, for instance. And English, we have the word condiments, but then, the word cheshni just doesn't cut it. Anyway, let me just skip these. So it turns out there's no need to code these transformations as rules of some sort. Okay, given enough what we call parallel text, machine learning algorithms will be learning these rules way better than humans can write them. What is a parallel text? Well, it's text where sentence by sentence, each sentence is the translation of the other one. Okay, and then we have 10 million of those sentences or more. Okay. So for the purpose of the next exercise, I'll assume you know English, but not Turkish. So pretend you don't, okay? So somebody tells you, here's a translation of each other, right? Geliyorum, I'm coming. Yeah, you have no idea how things work here. And I give you this. You say, aha, what is common here? Okay, so there is this part that is almost this part, okay? And that probably should be what is common here, okay? And then once you get that out, you can say, aha, gel means come, yaz means right. That's the correspondence. And then this part, yorum, uyuyorum, whatever, is the IM and then ing part. Okay, so I gave you 2 examples and you created your first rule. Then I give you, that's what you know, I give you this. Then you say, aha, since I know what iyorsun, so I know what gel is, so the interesting part is iyorsun part. So maybe iyorsun is you are ing. Okay. Now you have Eorson, you are ing, you have I am ing. So maybe you can do a little bit more analysis and say, means I am, sun means you are. And then the Eor part is the ing part. So that explains everything, that this set of things I learned. Okay. So far, so good. I mean, I typically do this with non-Turkish speakers. It's more fun. Okay. So I know these. Now I do this one. Okay. So, well, I get the same thing, right? Us means we are. Everything else works out properly. Now I have gelmiyorum. Okay. So, I said everything else works. And then I got this extra thing on one side, extra thing on the other side. So that M is not. Okay. So far, so good. Now you can take this much and now translate this, although you never learned about this explicitly. Okay, so you can say, I'm not writing. Or this one. Okay, so that's the simplest example of the basic idea of how you learn to translate. Except you have 10 million parallel sentences like these. Okay. You feed them into the machine learning system that learns to, you don't have to tell them, like, if there is an ambiguous word or whatever, it will just figure the damn thing out. Okay. One interesting thing is, for instance, English he used the phrase key feature, right? Key feature of this product, etc. That is translated into Turkish as not the anahtar özellik, but kilit özellik. Okay, and in no dictionary you will find the word key translated as kilit. Okay, but this will learn that because it just sees examples of that. It's only in that context that the word is feature and the previous word is key, etc. So you can take this. It will take a week of heavy-duty computing to build a translation model. Sentiment analysis. This is, again, a socially important thing. Distinguish between objective, subjective statements, news versus opinions. Find the polarity of statements. Is it a good one? Is it a bad one? Tricky usually. So if you see the word, this new laptop design is hot, that's a good thing to say about a laptop. The new laptop gets very hot is a bad thing to say about a laptop. So it's not just words. You have to do a little bit deeper analysis as to what's happening here. Hundreds of film reviews, even Turkey. I mean, I think there's a huge database of film reviews that people experiment with. And all the websites that recommend you movies would probably base their recommendations on things like those. Okay. Anyway, so this is, again, pretty old, about 9-10 years. And this is how tweets across various United States, in the United States, how they're classified. Are they positive or negative? Note that as time goes, there's a non-trivial color change. People get frustrated, angry. They're in traffic sitting and tweeting like, I hate this and blah, blah. Okay. I gave the URL here, and there's actually a video of how this rounding. You can look at that later. I'm not going to run the video here. That's sort of the original social application, social science application of NLP. This is pretty active still. They get about 92% correct for English, but this is complicated by all the stuff I mentioned about the language change. So people don't care about how carefully they type words, so spelling errors are rampant. This is especially true about Turks writing tweets around the world because they're using keyboards on mobile devices built for different countries' languages. So there are like 10 different variants of A, 10 different variants of the I, with the dot, without dot, with the cap. People don't care, they just type, and you see the crap that comes out in these things. So it's complicated by non-linguistic issues of keyboard entry and so on. NLP in the 21st century. So there are a lot of opportunities. Internet is a problem, but also an opportunity. There's huge amounts of text. Okay. There's significant strong computing power, huge server farms, these things we call GPUs that are used to build these machine learning models. But now there's a backlash because these machines literally consume a year's worth of electricity of a small city when computing these models. So there's now an ecological issue that people are bringing up. So yes, you're getting a 92%, but you're wasting a lot of energy. It gets a lot of carbon into the atmosphere. So can we do this with a smaller amount of computing and so on? What happened here? Okay. And then this whole new technique called deep learning is really killing it. Okay. There's strong market demand. New fields like legal, social processing are coming in. Challenges, languages are evolving, so you have to keep up. Okay. This is really happening. I mean, so think about Turkey switching from the Ottoman Turkish lexicon in the early 20th century into the current lexicon. Okay, that happened over maybe several decades. Okay, here this is happening literally real time. I mean, Zoom was not a word with the current sense 2 years ago. Now we say, let's Zoom. And we're clearly not taking a telephoto lens and working on it. Okay. So language is really rapidly changing. And the field, fortunately and unfortunately, is changing so fast that a book written about 7 years ago is now obsolete. And the authors cannot revise it because they cannot catch up. That's kind of how things are going there. There are languages that are dying, and there's a lot of work in I wouldn't call it linguistics, sorry, computational linguistics, but I wouldn't call it NLP, but more like computational linguistics. They're trying to recover these languages, and there are many of them in Turkey, for instance, that are not on this bandwagon of processing. All the languages in the Karadeniz region or southeast and dialects, so on, they are all kind of disappearing. Okay. Big push in solving, helping social political problems. One of the most interesting applications of machine translation was to build a system that would work without internet on a cell phone in places where there was no internet, there was no power. For instance, when an earthquake has happened and you fly in people to help with the recovery efforts, and they don't speak the local language. Okay, so you need to be able to talk to them and show them the text, and they respond, and you understand, so that your work proceeds easier. Okay. So just to finish up with social sciences, a lot of work. I was surprised in the last several days I've been looking at this. So there is actually reasonably regular workshop on NLP and computational social science. So I went through them, picked up some topics. But before I do that, I should give you how normally these disciplines should interact, just in case you guys. So maybe you're affiliated with some universities, maybe there are people in their computer science departments and so on who are working on natural language processing. How do you talk to them? Okay. On the social science side, you have to describe the problem. What is it that you want? Okay. So I'll give you some examples, I mean, from the papers, but you need to describe, okay, I have a text. I want to find out if a text has a certain property or if certain things happen in a text. Okay. What is the input? What is the output? What are properties of the output that you want? Sample examples so that the person can place that in his side of the things and see what kind of solutions can come up. Everything is data driven these days, so you have to compile the relevant language data, texts, tweets, reviews, political writings, whatever your application requires. Okay. You will have to annotate examples of phenomena you would like to extract, study. Okay. Okay, you say this sentence is a fake news example. This sentence is hate speech. This sentence is where the gender is used incorrectly. Okay, so those kinds of things, depending on your application. So those are the minimum of what, from your side, you would have to bring in. Other people would say, okay, let me take this description, let me formulate this as a problem on my side of the fence, and maybe come up with stages of tasks that I need to do so I can do this analysis. Okay. So you get the data, he takes the data from you, he or she trains the data to build up these tools. Then you run it on new data. You will have errors. With your social science colleague, they would have to work together to do error analysis. Why is this wrong? Maybe there is no example of that phenomena in your data, so the machine didn't learn it. Okay. So it's an iterative process, right? You go until you get to a point where you say, I can live with the quality of the system as such. Okay. So some sample papers from 2016. You can click on here. I'll give you the slides later. And okay. So this is about humans labeling other people and some NLP approaches to that problem. Okay. Author traits and influence detection. Okay. These are people I assume quite influencers on whatever these media are. and you can read their profile. Maybe their profile has some keywords. Okay, so you relate those to their influence. Okay. Political discourse on Twitter, and then, you know, are you on the Trump side or are you on the other side? You know, you can figure those out. Protest event mining. It's very important. I think there's a group in Turkey that is doing this. I think it's Koç University.
Yeah, they're presenting tomorrow.
Yeah, Ali Hürriyetoğlu and so on. I worked, well, I kind of was an advisory role in that for a while. Okay. 2017, similar papers, gender prediction on Twitter. Okay, somebody's writing tweets. You know. Language independence. So, okay, one thing that is important in NLP is if you can build your tool so that it is not specific to one language, it's better. Okay. So you build the tool part, and then you can specialize it based on specific data, as opposed to building a specific tool that is geared to one language. Okay, so that's language independent. You will see that. When does a compliment become sexist? Okay, so this is, again, social issue that manifests itself in text on Twitter, hence NLP. Okay. Topic classification. I just mentioned the classification, right? So the same problem. You have now political texts, and it's, you know, some of them I can't imagine what they are though. 2019, geolocating political events in text. Now you have text, you have events. Now where did it happen? If the tweet doesn't have a location indicator, you may want to triangulate that from other tweets of the same person, for instance. And okay, well, then that's the neural network now coming in. Prediction of censorable language. Okay, whatever that is. Now you build a system saying, here's an example of a censored language. Here's one that is not. So you have 10,000 examples of that, and neural network learns that. This is, I forgot to change this. Okay. Okay, so this is for like group decision making, predictions about that. Sociolinguistic study of online echo chambers. I assume echo chambers, right? People talking to each other, kind of positive feedback until it explodes. Okay, so it's and then 2020 is now very interesting. Okay, COVID stuff comes in, a lot of issues. So I miss you, babe, analyzing emotion dynamics during COVID-19 pandemic. Then people are anxious, are depressed, and have suicide risk. So you want to figure them out, and so on. This is a big problem in the US. There's a lot of bias in parole hearings for people coming up for parole. So people want to predict these things based on the transcript, so that they can inform the relevant authorities, saying, hey, blacks are, you know, 10 times less likely to get parole than whites, for instance, and so on. So additional resources, if you want to do a little bit more, this is in Turkish. I gave it about 3 years ago at Boğaziçi. It talks about specifically Turkish, and not in terribly technical, but kind of a historical perspective of why Turkish is interesting, and what has been done and where we are and all that other stuff. About hour and 40 minutes if you can afford the time. That was before we didn't use Zoom. I was in Albert Long Hall at Boğaziçi campus. So I would recommend that. Then more classical techniques talk in Turkish again. I gave last year at Bilkent Summer School of Machine Learning. This is from a computer science perspective, not necessarily. So it's reasonably technical, okay, but certainly accessible. I managed to came across this tutorial on NLP for computational social sciences by Lillian Lee and her student at Cornell. Looks like, I mean, this is pretty recent, maybe 5 years old or whatever. Gives you a decent perspective on it. One thing I didn't put here, but maybe you already know about it. There's a nice Python library called Nltk, Natural Language Toolkit, which is quite easy to use if you already. I would recommend that to build non-machine learning based systems, let's say. Okay, simple parts. Murat and I, over 2 or 3 years ago, compiled about 30 years worth of work on NLP that our groups and other people did over the many institutions we have been with. This is about 400 pages or so. I think the book is already a link to Amazon. Okay. So that's what I have. I'll be happy to answer questions. I'm killing time in New Jersey here, so I still have the time, but it's 7 o'clock for you. Yeah. So I leave it up to you. If you have questions, I'll be happy to either answer if I can, or just go off a tangent to see what happens.
Thank you very much. This was really, really incredible. I don't want to abuse others' chance of asking questions. So let me first give the floor to the participants. Do you guys have any questions?